Let us discuss this very important theorem. We call it as Fermat's theorem. It states that if the function is differentiable at c and it has extremum at c, then f dash of c is equal to 0. What is meaning of extremum? That means function has either minimum or maximum value. So it's very important theorem when we solve the examples. Okay, so let us discuss its proof. What is a given thing? Function is differentiable at c. So what I have done, I have written the definition. Okay, so function is differentiable, that means its derivative exists. So that's why left hand derivative, right hand derivative are equal, and that is equal to f dash of c. The second important thing is function has extremum at c. Okay, function has extremum at c. So that means either it has maximum value or it has minimum value. So without loss of generality, I have assumed function has a maximum value at c. I have shown here in a diagram. Getting? So we have assumed function has a local maximum at c. So therefore, by definition of maximum, local maximum, what can we write? So I can write, therefore, for very small h, okay, very small h, okay, belongs to R, what can we write? F of c greater than or equal to f of c plus h. We have written very small h since it is a local maximum. Getting? Local maximum, you cannot take much larger h, otherwise you will go outside the region. So function has a local maximum, that means in a neighborhood of c, function has a maximum at c. If you go outside the neighborhood, okay, so it will not be a local maximum. So that's why we should lie in a neighborhood. So that's why I have taken a very small h. See what is happening here, c is here, suppose c plus h is here. Getting? So f of c will be here, right, and f of c plus h, its image will be here, f of c plus h. Since function has a local maximum at c, what we get? F of c is greater than or equal to f of c plus h. Let us shift f of c on that side. So what will you get? 0 greater than or equal to f of c plus h minus f of c. Let us write it. So therefore, f of c plus h minus f of c less than or equal to 0. I will call it as inequality number 1. After that, see, there will be two cases. The first case is h is positive and the second case is h is negative. So yeah, let us write case number 1. Okay, case 1, h is greater than 0. See, if h is positive, as you can see in this diagram, h is positive. See, what will I do? I will divide both sides by h. See, h is positive, so that's why if you multiply both sides or if you divide by positive real number, inequality will be same. So therefore, what can we write? Therefore, f of c plus h minus f of c divided by h less than or equal to, same inequality will be maintained, 0 upon h you will have 0. 0 upon any non-zero number you will have always 0. After that, what will I do? I will take a limit on both sides. Okay, so taking limit h tends to 0 plus. I am writing 0 plus since h is positive, so that's why it will approach to 0 from right hand side only. So what I am doing, I am taking right hand limit of both sides. So what will happen? So therefore, limit h tends to 0 plus f of c plus h minus f of c divided by h less than or equal to limit h tends to 0 plus 0. See, have you seen it anywhere? Yes, definitely. In equation number 1, see, we have called it as 1, so I will call it as 2. See, in 1, we have already mentioned what is its value. Its value is f dash of c. We have already mentioned. So, therefore, what can we write? F dash of c is less than or equal to. So, if you apply limit to 0, but 0 is there. So, if you apply any kind of limit, you will always have 0. So, I will call it as 3. So, this is inequality number 3. So, what we have got, f dash of c is less than or equal to 0. For this case, we have got. So, obviously, we are going to discuss the second case, where the second case is h is negative. Okay. So, you can make a screenshot of it. After that, we will go for the next case. Okay, so second case is h is less than 0. Okay, so h is negative. What will I do? I will repeat the same steps. I will multiply both sides by 1 by h, or you can say I will divide both sides by h. But h is negative, so if you multiply any inequality by negative number, inequality will get changed. So therefore we will have f of c plus h minus f of c divided by h, inequality will get changed, greater than or equal to 0. So let us take limit of both sides. Taking limit h tends to 0 minus. So that means h is less than 0, h is negative. So obviously it will approach to 0 from left hand side now. So that means we are taking a left hand limit of both sides. So what will happen? Limit h tends to 0 minus f of c plus h minus f of c divided by h greater than or equal to limit h tends to 0 minus 0. So have you seen it anywhere? Yes, definitely. Its value is f dash of c from equation number 1. So we can write f dash of c is greater than or equal to, if you apply limit to 0, you will have obviously 0. This is equation number 4, inequality number 4. See, this part already you have taken, but see, this part is required for this part. So that's why I kept as it is. So in second case, what we have got, f dash of c is greater than or equal to 0. In third inequality, we had got f dash of c is less than or equal to 0. Here, greater than or equal to 0. So that means f dash of c is equal to 0. Okay, so that thing I am going to write. Just simply make a screenshot of it and then we will go further. See, from 3 and 4, we wrote f dash of c is equal to 0 and we get the required result. Okay, thank you. We'll stop here. Bye bye.